So the topic for today is Raft, replication protocol that we'll discuss in quite a bit of detail. In fact, we're going to spend multiple lectures on it, and one because it's sort of one of the core elements of and examples of an distributed replication protocol. So today I'm going to mostly focusing on the material that is necessary for labs 2A and 2B. So the election of the leader as well as pushing the logs around. And then next week we're focusing more on 2C and 2D, namely the snapshots and the lock compaction, and gives us opportunity to discuss any other aspect of Raft. In fact, we'll talk about Raft one more time in the week after. We'll have a Q&A lecture on 2A and 2B, and so we'll talk about the actual solutions to the labs 2A and 2B. Okay, so that's the plan, and so I'm going to just dive in with the starting point for today. The place probably to start is to observe that in some of the previous case studies of replicated systems, we've seen a sort of a pattern. You look at GFS, MapReduce, virtual FMFT, they all have a single point of failure. So even though they're replicated systems and they do replication for fault tolerance, all of them actually had a single point of failure. In the case of MapReduce, it was the coordinator. In the case of GFS, the master that hands out the leases, for example, and in the VM FT case, it's the storage server, or really the test and set server. And the reason, why, as we discussed in the previous lecture, the reason that actually there are single machines instead of replicated machines is to avoid the split brain syndrome. And for many systems, sort of, one way is sort of a bummer, correct? We're building a high performance, we're building very fault tolerant systems, and on all of these designs, actually, we do actually still have sort of a single point of failure, even though where replication is used for many other aspects of these system designs. And for many of the systems that we talked so far about, this to avoid this split brain syndrome and actually introduce a single point of failure or maintain a single point of failure, that's perfectly acceptable in many cases. Because in many of these cases, like if the storage server or the master goes down, hopefully it's only a single machine, so the chance that it's going down is smaller than any out of the chunk servers, and probably there's somebody ready to be beeped up in the case that the master goes down, comes back up, and can really make sure there's only one master online. So many circumstances is perfectly fine. That will lead maybe to a very short downtime. But in some systems, it's really nice. It would be really nice is actually if this we didn't even have to have two single points of failures. Basically, we could reduce downtime even further and increase uptime. And so, and that's really where the protocols, the style of protocols that Raft fits into come into play. But just before diving into or talking about sort of the key ideas in the protocol, let's remind ourselves why this sort of single point of failure leads, or why actually replicating the sort of crucial single point of failures like the test and set server can lead to this split brain problem. And so you might think, why just not replicate the single point of failure too? So let's try to do that, and then we'll quickly see what the problem is. So let's replicate the test and set server. And so let's do a simple, just a straightforward case. We'll just have one replicated, one test and set server, that's one, And here we have S2. That's the other replicated test set server. And just to remind, correct, like test and set takes an argument new and it returns the old value. And the goal is that if two clients at the same time call test and set, one wins, gets basically false back as the old value, and the other one will lose because it will get true back as the old value. So let's see how this might play out. So we have a client that calls test and set, and communicates with the first server.
What?
Communicates with the second server. And we don't really know, actually, it doesn't get a response from the second server. And so there's sort of two cases now, right? Where, why, if S2 doesn't respond, there's two possible reasons why that could be the case. So one case could be S2 didn't respond because S2 failed. And in some cases, in that scenario, really what we'd like to be doing is that at that point, basically C1 just declares victory, since nobody else can actually observe the value at S2, we should be done. We could proceed. But the problem is that there's the second case, and the second case is that there's a network partition. There's a network partition between C1 and S2. So in that case, really, C1 cannot proceed because there could be another client, C2, and actually communicating with S2. And it would be terrible, correct, if C1 proceeds in this case, because it might then update S1, get basically the false value, think it succeeds. But at the same time, S2 communicates with S2 and also succeeds doing the test and set. And so now we're violating our contract of the test and set. And so this is this issue of this split brain. Like when there's a network partition, we can end up in a situation where both servers are up and running and serve a different subset of the clients, and thereby violating the contract of the specification of the system that we're building. And the real challenging part here is that C1 just cannot tell the difference between these two situations. It doesn't know whether it actually is, S2 is not reachable because it failed or because of the network partition. And so that's sort of the conundrum that's behind all this, these previous systems, and why they sort of use this single. Why they don't replicate, these crucial services that need to be up, to avoid, the split brain syndrome. So, what can be done about this? And really, the key problem here is what can we do about network partitions? How could we handle them? And so, there's a key idea that sits in Raft and in many other protocols that underlies basically the solution, or why those protocols actually might succeed. And really what it is, in sort of a nutshell, it is this majority rule. And just to give the example in the context of the test and sets in your server, instead of actually running the server with 2 replicas, which I conveniently did, I'm going to run it with 3. So I'm going to have S1, S2, and S3. And the rule now is going to be that, like, a client can consider an operation succeeded if it at least can update a majority of the servers. So in this case, we can send messages S1 for doing test and set. We send a message to S2 for doing test and set. Then we get back positive responses, from both of them, like a false in both cases. Then we'll return false to actually the application, and the application can consider the test and set succeeded. And of course, we do it also to the third one, but the third one may actually, the message actually might not arrive, or the server might be down. We don't really know, but actually we don't really care. Because consider this following scenario where we have the second client also trying to do a test and set. Well, to be able to succeed, it has to talk to a majority of the servers. So whatever majority is going to talk to, it is going to include either S1 or S2. And for S1 and S2, both of these operations actually have succeeded by SC1. So S2 or C2 will always observe the result of C1's operation because there's sort of an overlap. Yeah, and we'll see basically in Raft, this is exactly the same things, or it's roughly what's going on, right? Like when a leader accepts or enters an operation in a log of the majority of the followers, then it means that a subsequent leader that's going to come on in the next term, will also try to acquire a majority to get voted as the leader. And as part of that voting, there's going to be one server, one follower that actually has seen the last operation performed by the last leader. And so that is going to basically be the building stone on which we can build these fault-tolerant services that can handle network partitions and failures of servers while still achieving strong consistency. Another way to think about this majority business is that if the network partitions, there can be only one partition that has a majority. There can be no other partition that has a minority. And so only the partition that actually has the majority can actually proceed. Another way of saying that, another implication of that is, it could also be the case that there are multiple partitions and there's no majority anywhere. And in that particular case, the system can just not proceed, and clients talking to it basically have to wait until the network is healed enough that at least there's one that there's going to be at least one partition with a majority of services. Another sort of quick observation here is that, of course, you may want to get this particular scheme that I just described, the free servers, only tolerates one server going down, correct? If two servers going down, nobody can actually obtain a majority, and so therefore nobody can actually, no client can actually get the operation through. Clearly, it's easy to extend this idea by what typically is called like doing two F+1 replication. So if you want to tolerate F faults instead of one, you need 2 plus F1 plus server, so that at least you have always a majority if F fails. And so in the case of here F is 1, and so we're running with 3 servers. If you want F to be 2, you have 5 servers, et cetera, et cetera. If you want F to be 3, you have 7 servers. Okay. One other thing that's maybe important to point out, and that came up a lot in the questions, what is actually the majority? And the majority is the majority of all the services that are there, both the up ones and the down ones. And so when you take a majority, you don't take the majority of the 2 if there are only 2 alive, you take a majority of all the servers in the system. Any questions about this sort of key idea of?
Can there be an even number of servers? Like if you have 4 servers, would the majority then be 3?
Yeah, and we'll see that in a couple cases, correct? In Raft, that if the number of servers is reduced from 7 to 6, and because 1 is down, and you still want to proceed, you need a majority, but you still need 4 servers to actually proceed. But if you can get the 4 servers, then you can keep them going. Okay. Any other questions?
So I also have a question about the majority. So does the majority consider the server itself? So suppose in Raft, does like the server itself consider in this?
Yeah, it's part of it. So like, often we see in Raft, correct, that the leader votes immediately for itself, or the candidate votes for itself. And in the leader, when it appends, to its own log, it counts that as 1. So it's part of it. Okay, so there's quite a number of protocols using this idea, and sometimes this idea is referred to as quorums or quorum protocols. For the obvious reason, And there were sort of two, the state of the art for a long time until like the early 90s or late 80s was there's no protocol. So basically we were always in the situation of like this single point of failure. And then in the early 90s, there were two protocols that were invented roughly at the same time. One is called Paxos, which is mentioned in the paper quite a bit. And the other one is called view stamped replication. Sometimes called VR. And these were invented around 1990. They didn't actually get much attention at that point in time because people didn't really have a pressing need to be able to sort of completely automatic fault tolerant systems. But that changed in the last 15 years. So in the last 15 years, there's much use of these protocols. And in fact, sort of interesting to observe, correct, that is in the last 15 years. And that's basically, sort of 15 years after these protocols were invented. Yeah, so basically they sat on the table or sat on the shelf for 15 years until people actually had a real use case for them. The protocol that we're going to be we're going to be implementing in the lab, and we're going to be discussing in the lecture, and which is the topic of the paper, is falls in this lineage of protocol, and it's called Raft. And it was I think it came about, or it was written up in 2014. The paper's from 2014. And this is one of the more sort of complete descriptions. It touches on a lot of different aspects if you're going to build a complete replicated state machine, and explains those clearly. And so one of the reasons why we're using it for the labs and for this particular lecture. Any questions about sort of the history here around protocols before I dive into Raft? Okay. So before actually diving into Raft, let me first sort of talk a little bit about how one would use Raft to build a replicated state machine. Because that's in the end our end goal, and that will help reasoning about what Raft actually should be doing for us. And so the basic way you would use Raft, and we'll actually do this in lab 3, is let's say you have a server, and the Raft is basically nothing else than a library. And so in our setting, it's going to be code package, and you can write a replicated state machine by basically importing that package. So here's we got here's a Raft at the bottom, and you build a server using Raft. And so, for example, in lab 3, we're going to build a key value server using Raft. And clients talk to the key value servers, and submit put and get operations. And the key value servers, when it receives one of these put and get operations, it basically hands it off to Raft. And so it basically puts it to Raft and actually sticks it in what we'll see in much more detail. It'll put it in a log. I'll actually draw this slightly differently. So appends it to a log. Actually, it appends it to the end of the log. And then Raft internally is going to talk to other servers to basically replicate that log. And so here are some other servers. They're basically structured exactly in the same way. They have a Raft library component and a key value server, like in many other replicated state machines that we've seen. They're identical key value servers. And we're going to play the same game as in all the other previous replicated state machines we're seeing. We're going to basically feeding operations to the key value servers in the same order everywhere. And as a result, if the key replicas all apply the operations in exactly the same order, we should say the same key value store is being built, right? So we have a key value store here, whatever, key 20 has some value. We're applying the updates to this table exactly in the same order in all the replicas, things should be good. Right? We're going to have identical replicas. So the way Raft is structured is that one of the replicas is the leader. So in this, for convenience, that's going to be the first one on this site, and it just actually declines to talk to the leader. And then what happens next is that the client talks to one of the leader KV server. The KV server appends a log entry to the Raft log of the leader, and then basically communicates with the other Raft libraries, and then those Raft libraries do exactly the same thing. Basically, they append the operation to the log, to their logs, and send the response back to the leader. And of course, all this state is stored, the log and some other state is stored on disk, so that if any one of them fails, they at least have the last part of their log still available, and can build from there. So once basically, and we'll talk a little bit more in detail, but once the entry or the log entry is replicated on free servers, then they can actually be delivered in order to the key value server. So every committed operation, or every log has an index, or every operation has an index 0, or actually 1, 2, 3, 4, whatever, in order, and they're going to be delivered in order to the key value server. So once an operation is committed, it's going to be delivered to the key value server. The key value server performs the operation, maybe updates the key value table, and then actually the leader alone sends a response back to the client. So that's sort of roughly the sequence of events that happens. So client sends a request to the leader, inserts it in Raft, chit chats with the other servers. Once it's replicated on enough machines, then it's considered to be committed, and we'll talk a little bit more precisely what committed means. And then uncommitted operation is delivered to the key value servers, and then they execute the operation and respond to the client, or the leader responds to the client. So what happens on the failure? On a failure, a new leader is elected, and it will take over the role of the old leader. And so, for example, like in this particular picture, it might be the case that this leader crashes, and this becomes the new leader in the next term. We'll see exactly what that means. And then the clients basically fail over. They will see they don't get a response, so they will time out, and they fail over to the second leader, the new leader, and basically retry their operation. And so they insert, that new leader will take their operation, insert it back into Raft. The same things happens as before, and maybe this time we get lucky and we execute the operation without any failures. Now, if you think a little bit carefully about this, that does mean that a client operation might end up twice in the log, right? Because it actually may be the case that the first time it succeeded, but just didn't get the response. So it doesn't know that it succeeded. It will retry. This new leader will put the log, put the retried operation also in the log, and it will pop out, at some point at the key value servers, and then actually be a duplicate. And so, as you will see later in the lab 3, actually it turns out that you need to do duplication, detect duplicates. But that's mostly an issue for lab 3, so it's not going to be a main issue for now. But it's just important to know, that sort of this is the sort of general style in which one would actually use Raft to build a replicated state machine. Any questions about sort of how to use Raft for replicated state machines?
We have a question in the chat.
Yeah. What's the typical number of clients contacting the leader? Well, there could be many. There's no real limit on it. What you will see, it could be the case that a single machine can, maybe that's implicitly what the question is. It could be the case that a single leader, can just not tolerate is not capable of handling that many clients. And so what happens then is that basically the servers get sharded. You shard the key value servers in multiple Raft groups. So for example, shard 1 would be one Raft instance, shard 2 would be a Raft instance, shard 3 would be a Raft instance, and the clients talk to the appropriate shard to apply their operations. And in that way, one can scale the server to many clients. And in fact, that is what Lab 4 does. How does the client know how to communicate with the new leader after the old leader fails? The client basically has a list of all the servers that are in the system. So in this case, we're running with 3 servers. Everybody agrees there are only 3 servers in the world. The clients know about the 3 servers, and they try one randomly. And if that is not the client, it will redirect. If that's not the leader, it will redirect the client to the appropriate one, the actual leader. Yeah, the answer is quite.
Do we assume the servers are like in geographically close, close to each other, or could they be far apart?
They could, in principle, be far apart. There's no real restriction on that side. The only issue, of course, is if the servers are very spread around the world, the delays to actually get a log record appended, will take a little while, and so the delays will be long.
When is the log entry being executed in the KV storage?
Once it's committed by Raft. So once Raft has decided that enough replicas have received it, and it's no way possible that one has to back out of that operation, then it's handed out to the key value server.
So the leader will first execute this command, and then the leader will tell the followers that this command is committed, and then the follower will.
The leader knows, as soon as the leader knows that the operation is committed, it actually can hand it off to its key value server. Let's talk about it right now, and I'll go in more detail as we go. So like a bit more of an overview of the protocol. So previous board was sort of an overview of how you use Raft to build and replicate a state machine. Now let's look at the Raft itself a little bit in more detail. So here are some timelines. We got a leader, we got 2 followers. So we're running with 3. The client talks to the leader. The leader has a log, of all the put and get operations. When it gets a new one, appends it, to the end of the log. Then it actually sends it. Sends the log entries to the new log entries, to the followers. And let's say that follower 2, here's follower 1, here's follower 2. Follower 1 actually receives this log entry, everything is okay. It appends it to the end of the log. It sends basically an ACK back saying yes, I appended it. And at this point, in the Raft view of the world, 2 servers actually have the log entry, and so Raft actually, the leader can actually commit the log entry. And so at this point, the leader can actually hand off that request that it just received. It can actually hand it off to the KV server. And the way actually the lab does this, or the lab infrastructure does this, is that basically we have a channel, a Go channel, one single Go channel, where basically the Raft Go routines, and the Raft Go routine that actually decides that a particular operation is committed, it just sends that operation on the apply channel so that the key value servers can actually apply it. At some point later, so notice at this point that the leader basically has committed the operation, and it's perfectly safe for the leader to commit this operation, because a majority of the servers, actually the majority of the peers, actually have received the operation, correct? So that's, even if there was a failure and we elect a new leader, that's the case that that leader, or one of the servers that is remaining, actually has the last operation that was appended to the log by the previous leader. So everything is good. Of course, the last guy, the first follower, will also at some point respond and say yes. So at this point, basically, from the point of view of the leader, the operation is committed, except the followers don't really know it yet. because the followers, they only know that, they got it, and that the leader probably has it. But they don't really know. And so what actually happens is that the subsequent operation, so when another client request comes in, the leader will append another log entry and basically sends, a new operation or a new append entry, to the followers. And that append entry does basically two things. It, provides the new log entry for the new operation, but it also confirms that all the preceding operations, or tells us which operations actually have committed so far. And so when F1 and F2 receive, this operation, this RPC, they know that the operation has been committed by the leader, and therefore at that point they can also, deliver it, to their key value instance, and know that this operation is committed.
I had a quick question. So,
Yeah.
So when the leader sends an operation over and a server replies, does that mean that means it's in the log, right?
Yes.
But what happens if you get a majority, like a slight majority, and then one of those logs, like one of those servers crash? Like, do logs have to be in storage, like in disk?
Yep. So that's a
Okay.
very good question, correct? So the every change to the log, so if you look at the Raft paper in detail here, some state is must be stable, and the log is one of those pieces of information that must be stable, as well as the term number and a bunch of other things. And so if a server crashes, no big deal really, because the majority of the servers does have that entry on their disk. And when they come back up, they'll find it.
I have a question.
Yeah.
So what happens if, for example, follower 1 replies with yes and the leader commits?
Mhm.
Just before it sends the next command to the remaining followers to also commit, it crashes.
Mhm.
Now the remaining followers don't know that they need to commit because the leader has crashed. So wouldn't this cause problems?
They will commit it, right? Because one follower will have it in his log, and as we'll see in the leader election rules, it will become the leader, and it will propagate that append entry, to the other servers, and then they will apply it too.
Okay, I see. Okay, thanks.
Okay, so that brings me maybe this is a good sort of segue to the next topic on why logs, and because the last few questions
Sorry.
all about that. Yeah.
Actually, as a follow-up to the last question, so the server crashing, like after it has like consensus, crashing, right before committing, it could delay committing.
What
right?
do you mean? What do you mean with committing?
So like after it has consensus on a change, right? After it has a majority.
Yep.
It can, like the paper said, you essentially tell other ones, like other servers, you tell them, okay, this is ready for, or sorry, it's committed, it's ready for like execution right into the state machine.
Yep.
So if it crashes before it tells other servers that it's ready for execution, it could delay execution, right?
It could delay execution. Well, okay, so first of all, if the leader fails, at that point, nothing happens, correct? Like at least the clients can't proceed with any other more operations. And so basically, if you want a way to think about it, at that point, sort of Raft reconfigures itself, elects a new leader, and that's going to be F1 or F2. One of the two is going to be the new leader, and the other one is going to be the follower, right? And one of the two actually has received the append entry that the leader might already have committed. In fact, its KV might already have executed. No problem, correct? Because one of them has it. That one will become the leader, as we'll see later with the leader election rules. And that one will, submit it to its KV server and will replicate it, to the other follower, and then it will apply it to its KV server. So in the end, they all will apply all the operations in the same order.
I agree. Like eventually it'll happen, but it could be delayed, right?
Yeah, could be delayed. Absolutely. The new letter sends a complete log to all the followers. It will. The way it works is actually it will try to send the end of his log if one of the followers doesn't recognize the end of the log, it will back off and send more and more earlier entries. We'll talk about it later, but in the end, it could be the case that the leader will replay its complete log to one of the followers if one of the followers has missed all the log entries. Again, coming back to logs. So one reason you might wonder why you have logs at all is because, like, the KV server, has a database too, correct? It has a table with all its information. And so why do we need actually, sort of this information twice? One's in the logs and one's in the KV table. And so there are a couple of reasons for that. One, a couple that already came up in the questions, basically. One, for retransmission. So when the leader, sends one of these append entries, to one of the followers, that message might get lost, and so the leader must be able to retransmit it. So it needs to keep a record of all the log entries that are sort of in flight. Second reason, it's probably the primary reason first, is like we need order. Every append operation or every command must be delivered in the same order at the same and all the replicas, and the log is a very convenient way for us to actually maintain that order. So the second reason, retransmission. The third reason is we need a persistence. One of the followers might crash, or actually all of them might crash, and then they come up again, and we still need to be in a position that we can basically retransmit log entries to bring everybody up to date. And so the log must also be persistent. And then finally, we need sort of space for tentative operations or tentatively committed or for tentative commands. As we noted earlier, or that came up in those earlier questions, when the leader sends an operation to a follower, the follower actually doesn't really know at that point whether that operation will be committed. So it just must stick around for a little while until it actually learns whether that operation is committed. And so we need some space for these tentative operations, and the log is a convenient place to actually do that. In the end, what will happen, correct, is that the logs are identical on all servers. There may be out of sync, during periods of time. One might have more entries than other logs, but like if we sort of keep running the system and then stop the clients, then at some point in time, all the logs will be completely identical. And that means that basically those, since they all have the same order, all the operations will be fed, to the client, the KV servers in the same order, and the KV servers will all end up in the same state. Okay. Okay, let me talk a little bit about an individual log entry. So whatever. I'm going to draw many pictures like this, where there's a bunch of log entries, starting at 0, 1, 2, blah 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 blah. And if we look inside of one of these log entries, there's going to be a command, which we're mostly going to sort of ignore. We're not going to really think much about it at all. That's the thing that's actually being delivered to the application. So that's, for example, the put or the get operation with its arguments. And then and the second thing that's in there is a term. And this is basically the leader's term. So the term in which this particular command actually was appended to the log. And one way you can think about this is that basically the term identifies uniquely the leader that appended the operation to the log. Because during every term, there's only one single leader. And so the term ID really basically implicitly signals who the leader was that actually appended to that log entry. The number that goes along here, so if this is n, or maybe let me use I here, that's the log index. So the combination of a log index plus a term number basically uniquely identifies the content of that particular entry. There could be no two log entries that have the same index, the same term, and have different commands. Because only a single leader, could have been in charge in that particular term, and that leader, commits, appends operations. Will uncommitted log entries be overwritten? Yeah, they might get overwritten. We'll talk about it later, but that's certainly possible. Okay, so if we look at this picture, so there are two things that, in this part of the, I guess, an answer to this question, there are two things that need to happen. We need to elect leaders for a particular term, and we need to actually ensure that the logs become identical. If we have failures and we have leader changes. And so we're going to talk about both of these topics, and we're going to start with leader election, and then talk about the making logs identical a little bit later. Okay, election. Election is really the topic of Lab 2A, and really the story is in some ways straightforward. We have, say here we are a system of 3 entries. We have a leader in term 10. We have a follower in term 10, so we're sort of stable situation. Another follower in term 10, and let's say the leader crashes or gets partitioned from the network, so can't talk anymore. What will happen is that the followers will start an election, and the reason they start an election is because they're missing heartbeats from the leader. The job of the leader is to periodically, in a sort of fixed interval, send an append entry to the followers. Normally, that might be happening because a lot of clients are active, and so the followers continuously get append entries. But if the leader doesn't receive any commands from the clients, then it's actually supposed to send in a heartbeat periodically and telling basically to inform the followers that actually you're still the leader. And the heartbeat basically takes the form of a normal append entry, except no new log entries. And so the leader just tells it, the leader just tells in the heartbeat, like, my log is this long, and this is my last entry, and if those match, then everything is good. So if the leader fails, then after a couple of heartbeats, and we'll talk a little bit more in detail about this, there will be an election timeout. So the followers have a timer running, and they reset that timer every time they get a heartbeat or an append entry. But if they don't receive any heartbeats or append entries, then at some point in time after this election timeout, the timer goes off, and at that point, a follower starts an election. And just let's assume that the first follower reaches that point first, and what it will do, it will it will increase its term number, so it will set the term number to 11. It will talk to itself, if you will, and be part of the and will vote for itself, and then they'll contact the other follower, and we'll also try to contact the leader. They'll presume that the leader, let's say the leader's down, so the leader doesn't respond, but the second follower does respond, and so at that point it gets 2 votes, one from itself and one from the follower, and at that point actually it becomes the new leader. It becomes the leader for term 11. And then it starts, basically clients fall over to that leader, and the things just proceed as before. Okay. Now, maybe there's a couple problems that you might worry about, but one of them could be the following situation. It turns out there was a network petition between leader 10, or the leader for term 10, and the followers for term 10. And so at some point that network petition heals. And so maybe there are client requests, coming in still to the leader for term 10, and now, of course, now it looks like, whoops, we might have actually 2 leaders, and we're back into the split syndrome problem. That turns out not to be the case, because when the leader tries to actually, send append entries to the followers, to followers that are now in term 11, they will just reject, those append entries. And they will tell the old leader that, too bad, he's not the leader anymore. In fact, they'll send a message back, saying, no, I cannot do the append. And here is my current term number 11. The leader receives that, sees that the term number 11 is bigger than his term number 10, and basically steps down as leader and becomes a follower. It may kick off another election, or to basically become part of a term that has all three of them. But there's no chance of a split brain problem because you just can't actually get any operations through. So no split brain. And the reason that we avoid this split brain is because of this majority rule, as well as these term numbers. Okay, that's of course not the only problem that we might have. Another challenge is we might end up with split vote. So like with this particular picture, we had our leader, maybe he was leader in 10, it's partition of the network. Here are our two followers in 10. And if we're not careful, maybe they will actually start, elections very close to each other. And so, F10, votes for itself. The first follower votes for itself. The second leader of the second follower votes for itself. Then, they send, vote requests, to each other. And the rule is that, you can vote one vote per term. So when the first follower has voted for itself, it has voted for itself, and so when it receives the second vote request, it actually cannot vote for that vote request because it already voted for itself. And so at this point, we're going to have a split vote. Like this guy is going to have one vote, and this guy is going to have one vote, and they won't do anything. But at some point again, later, there will be a timeout, and then this process starts again. And of course, as part of that process, this is election 11. Election 11 resulted in 12. It will actually go to election number 12, and try to do this again. Now, if you're not careful, correct, this could just happen over and over, endlessly. Basically every time the two followers was roughly at the same time start this election, then we're not going to make forward progress. And so, way to avoid this problem is that the election timers are randomized. And so when the followers set their election timer, in the paper they talk about like picking a value between 150 milliseconds and 300 milliseconds, a random number in that interval. And every time these followers basically reset their election timeout, they pick a new number, a random number in that interval, and only when that timer then goes off, they run the election. And if basically if this interval is wide enough, that it's unlikely that like the first person or the first follower that actually gets the first follower whose election timer runs out, the interval is wide enough that there's a good chance that it actually will succeed, completing a complete election before the second timer goes off at another follower. And so this avoids this sort of endless split vote. We might get unlucky and we get maybe one or two split votes, but like over time, there has to be the case that we in the end will succeed. There are a couple sort of, and this is important maybe for the lab too, there's sort of a couple pressures on these election timeouts. You don't want to pick an election timeout that is too short. right? Because if it's too short, for example, shorter than a heartbeat, then you might lose one message and immediately you start running an election. And nothing bad happens because we'll elect a new leader, you will go through a new term and all that kind of stuff. But then basically, during this election, the system is actually not usable, right? The clients are actually blocked. So you don't want to unnecessarily cause elections. And so one of the things you want to do is basically probably take a value that's at least bigger than a few heartbeats. Because we're maybe in a data center, we'll take a few milliseconds to do an RPC, and we may want to wait at least, so maybe 3-4 RPC round trip time so that we get a chance to retry an RPC without actually having the election timer go off, and so that we can cover from like temporary network failures. Then, we want to presumably add, some random value to that. Random value to avoid the split votes. And so on one hand, we want to make the random value as big as possible, right? Because if we make it big, then there's very little chance that actually we will run into a split vote problem. But the other hand, if we do that, then there's a chance that the system may be down for a longer period of time. We might pick a big value for the election timeout, and that means downtime from the point of view of the clients. So we want to keep this short enough that the downtime is short. In the paper, in the lint and eval section, does quite a bit of work on sort of validating what are some reasonable values for their particular setting, and then that's how they got to the 150 to the 300 milliseconds. In the lab, we're going to be reasonably generous. Basically, if you sort of recover within a second, you're more or less going to be good for our test cases. Okay, I want to make one more point about the elections. So another scenario that is sort of important to consider is we have a follower, we have a leader, the leader goes down. So there was 10, this was 10, here's follower 10. And we already talked a little bit about it. When, let's say this guy goes first, it votes for itself. And the protocol records, on stable storage, who it voted for. So the records on so if this is follower 1, this is follower 2, it'll record it voted for in term 11, for follower 1. Why is it recorded on stable storage? And why does the follower need to remember that that it voted in term 11 for itself?
This way it doesn't vote twice if it fails.
Yeah, it might crash, right? Like right here, and come back up, and it should remember that and somebody might have, let's say it was actually there's a third one guy in here, follower whatever 3, and it already voted for follower 3, then it can actually not change its mind, correct? And so, because in the end, at the end of the term, we have to be in a position that per term there's only one leader and never 2. And so, to ensure that every follower must remember for which candidate it voted and never change its mind. Okay, I guess there's a whole discussion in the chat about the timeout numbers and in relation to the lab. So people can look there if they are confused about this, or otherwise we can talk about elections a little bit more, because this is about the last thing I want to say about elections. Any questions about elections?
I have a bit more general question. So in like the figure 2 of the lab, it says that for each server, you're storing like the current term and then who it voted for.
Yep.
But not the like current state of the server, like if it's candidate or follower or leader. So I'm wondering how they like, is that implied or is there another way to figure that out?
I guess when you come back up as a follower, and you start an election, and then that will, in the end, at the end of the election, you know what you are. You're either a follower or the leader.
I see. Okay, thank you.
Does it make sense? One warning about figure 2, both a positive and then there's maybe a negative statement. Anywhere in the figure 2, when it says like, you should do this, you should really do it. So you cannot omit any detail that actually is in figure 2. If you do that, then undoubtedly you're going to fail some of the test cases. Unfortunately, figure 2 is not complete. And so you still will have to do some thinking. So particularly like figure 2 doesn't really say that much about like how the replies are handled of the vote RPC and the append RPC. And so you will have to do some thinking sort of to fill in the missing details. And so there's 2 points here, like figure 2, anything that's in there, you better deal with it. But there still might be things missing that you will have to resolve for yourself. You'll be looking at figure 2 a lot.
So from the description of the election process, there seems to be, like even for lab 2A, which deals only with election, there seems to be some state that we need to store on persistence.
Yeah.
So like, for example, like who you voted for and the term number.
Yeah.
But when you look at the code of lab 2, all of the code that has to do with saving the persistent state, it says above at lab 2C. So is it that it's not that crucial maybe to care about persistent storage, or should we absolutely start implementing persistent storage?
Yeah, I think in the first couple of tests, we don't actually crash machines. And so therefore it's not important. And in 2C, we're definitely crashing machines.
Okay, awesome, thank you.
Okay. How we're doing? Everybody on board? Okay, here we go. Next step. Okay, so one important thing to realize, and this came up earlier in the questions, and I want to hit that now, that topic hard, is that logs may diverge. And they can be quite dramatic, but just let's get into it for just a basic understanding, and then discuss it in more detail. So let's do a couple simple examples. So I'm going to write things using the following notation. I'm going to have 3 servers, as before, but I'm going to cut all the timeline business and just like draw the logs. And we have indexes. So let's say these are indexes. There's a preceding part to it where we're talking about 10, 11, 12. And so, there's a term entry in each one of them. So let's say all 3 servers committed or appended an operation in term 3 to index 10. And, and the same thing happened in with index 11. So one way you could get this correct is that server 1 would be the leader. Server 1 appends it to its own log, then replicates it to S2 and S3. Same thing happens for index 11. Then index 12, maybe it's also successful. It appends one operation in that index for its term. So that's term 3, but then it crashes. Right? And so now we're in a situation where one server actually has an extra log entry in its log and the other ones don't, or maybe one of them has it too, but they're definitely not identical. So that's a simple case, correct? Like nothing really spectacular going on, but there's much more interesting cases, going on. So another case could be, one server, again, S1, here we go, same scenarios, S2, S3, and let's just say we have the following logs. So this is the situation. We have in index 10, we have entries at all servers for term 3. In index 11, the first server has no entry. The other two have an entry for term 3. And then last one, number 12, we have entries in index 4 at servers 2 and 3 with term numbers 4 and 5. So the first question that we need to ask ourselves, is this possible? Can Raft end up producing logs in this way? Where in the same log entry, we have two different term numbers in the same log index.
Yeah, that's possible. So basically, it looks like.
So like, what is the scenario that produced?
Yeah, so it looks like server 2 or server 3 was the leader for term 3, and then got some logs out to server 1, and then shared another log with only one of the two servers.
Yep.
After which point it went down. And then S2 got elected as leader for term 2, which is still possible because its log is like up to date as up to date as the others. And then
say that again, just to make sure. So S2 got elected for term 4, right?
Yes.
Okay, not term 2. Okay, so S2 gets elected for term 4.
Yeah. And then
using S1 as a backup, correct? Basically as the follower.
Yes,
Yep.
I think.
Yep.
And then S3 gets elected for term 5 before S2 can put anything in the logs.
Yeah, or another way of saying it, like maybe S2 crashed right away, correct? After it got elected to term 4. And so then there's a timeout. Then let's say S3 was petitioned, but now it's back. And at that point, it will become, it can come into term 5, correct?
Yeah.
Okay, good. So that's possible. So it turns out there are quite a bit of wild variations possible. So if we like look at the, so here's the figure 6, for figure 7, sorry, from the homework. Oops. And the homework asked basically questions about the form, like, well, what happens to like this guy in the figure 6 itself, or figure 7, whatever it is. I think it's figure 7. The scenarios being discussed is like this guy becomes the top one, becomes the new leader. And in the homework, we asked the question, like, what happens if this leader just goes away? And what are the possible outcomes? And the possible outcomes like are, so for every log index, the question is, which one gets rejected? Which one will be accepted for sure? And which ones depends? And I think this is an important exercise to do, because once we sort of understand what all log entries are possible, what are possible outcomes, it will really firm up like our understanding about how Raft actually is supposed to be operating. What I'd like to do is like do a quick breakout room, and I'd like you to identify two possible outcomes that are not guaranteed in the corresponding scenario. So let's take a quick breakout room session here, and let's try to figure out the answer to the homework question in 5 minutes. Really, were you able to?
Franz, do you want me to do it?
Yeah. Oh yeah. Well,
Yep.
Let me actually make you. Participants. Make host. Okay, Lou, you're host.
main ones.
Okay, can everybody hear me again? Can I get a positive signal?
Yes.
Okay, super. Okay, so I hope everybody had a good time discussing this. And so so this is really a discussion about log divergence. And we see here, correct, in this figure, there are pretty wild variations in what can happen. And these are all possible, as the caption of the figure explains, they're all possible scenarios. And so the question in the homework, and just to quickly review that, I'm sure most of you already.
I don't think we can see your screen.
Oh, that'll be too bad. That's because I forgot to click share. Yes. Okay. Let me fix that. I appreciate that. I gotta. Okay. Everybody can see my screen?
Yeah.
Okay. Okay. Thank you. Sorry for that. Okay. So going back to this caption of figure 7. Figure 7 explains like these are all possible situations, and what we want to figure out, before talking about the details about how the logs get repaired, what actually is possible. So assume that actually this top guy did not get elected leader, so in the caption of in the figure, but like basically what outcomes are possible. And they're going to be, what I mean with that is, like, for example, we look at F, it has an index of an entry from term 2 in index 4. And the question that we want to ask and understand is that clearly this is possible because this could have happened. What will happen next? Is it possible that this entry will survive? So when we reconfigure like the leader, basically, logs being put together in or synchronized, or the leaders force the logs to be identical. Is there a scenario in which actually the log entry, the entry from term 2 will survive?
No.
No, correct. This will definitely be rejected, correct? And why is that the case?
There's entries from term 6 that are already committed. And so F will never be elected.
Yeah, F will never be elected. And so somebody else will be elected, and nobody has a 2 in term 2 in index 4. So it will be overwritten. With what value will be overwritten?
There will be a 4 overwritten.
Yeah, this will become a 4, correct? So when later on, when we talk about sort of log, synchronization, or forcing logs on followers, it has to be the case that this 2 turns into a 4 at F. Good. So this also answers sort of a second question, like, the entry from the index 4 from term 4 is definitely going to be accepted. Okay, then maybe more interesting is this question about depends. So we know at least one entry term that definitely going to reject it. We know one term that's definitely going to accept it. And are there any sort of terms and indices that may be possibly accepted?
The 7s, maybe.
Yeah, the 7s. So when would the 7s not be accepted? Okay, so the easy scenario is the 7s will be accepted, correct? Because D gets elected leader, and then it will force it log on everybody else. Right, so that's the case where 7 gets accepted. When does 7 get rejected?
If C gets selected leader and then D is down and
Yes.
it is overwritten.
Yeah, so D goes down, C becomes leader, and then C's log entries are being pushed on everybody else entries. And then whenever D, and so then we're going to be turn 7, correct? And at some point that will be longer. And whenever D comes back up, its entries are going to be overwritten, right? So 7 is also. So 7 is definitely possible, but not guaranteed. Any other case?
I had a question. A could become leader too, right?
A?
Yeah.
A could get leader if C and D are down.
Wait, C and D
if
don't even have to be down for it to be elected leader, right? It just has to get
if
votes
it's
from
the
a
first one,
majority.
yeah.
If the longest log, correct? If the two terms are equal at the end, then you pick the longest log.
But I think if A is the first one to call for an election, right? Like potentially B,
Yeah. So if C,
EF, right?
yeah, if C and D are down, A could win the election.
But if they're alive, can't it also still win the election?
So let's say C and D. Okay, let's D is down. Let's do that for sure, correct? Because we know that D will win the election. Period. If D is up.
Does it have to? Like we know it won't get a vote from D, right? For sure. But does it have to win?
Well, what do we think?
I don't
what
think.
if A received the vote from B, E, and F first, and then received the vote from D?
Yeah, you can get a majority, correct, without actually D participating.
Mhm.
Even if D participated in the election, it's possible for A to get the majority vote, right?
Yes, I think we just answered that.
Isn't there a mechanism though where if a candidate sees a message from another server with a higher turn number, it like stands down?
From a higher term,
yes.
from a higher term number, but A has to, if D is down.
It doesn't have to be down, right? You just have to get them first.
Yes.
It just has, yeah.
Exactly.
But it will step down when it gets to vote from 7 or D.
Wait, are you sure about that? Because I don't think so.
Yeah, the current is 8.
Well, okay, so if D at some point will, it depends, they're going to start racing, correct? Okay, let me actually, this is a very important topic, so I don't want to do it in 10 seconds. And let me come back to this at the start of the next lecture, okay? This is a great point to stop.
I think the state machine in figure 4 clarifies it. Like a candidate goes back to follower if discovers a higher term. So if D wasn't down, it will go back to follower. It won't try to elect itself.
Wait, but I thought that it would only go back to a follower state if it received and append entries from a current leader. Like a request vote is not the same.
So it's worth knowing that there's a difference between the term number that a server's at and the term of the most recent entry in the log.
Oh yes,
you can
that's
have,
also true.
Like server A can have most recent entry in the log be a term 6, but have its current term number be 7. And
its term number can actually be arbitrarily high.
Yes.
Correct. That's correct. And so A could start term 8 and then get elected in term 8. And whatever D tells it doesn't matter, because if D's most recent term is 7, A won't go back to follower because it's a higher term than 7.
Oh, I see. So it could be a higher term, arbitrary high.
Yeah.
Wait, could A go into term 7, its own term 7, if D was like partition, like if there was a network partition and it didn't know about D?
Wait, I'm so confused. Like, even if it does know about D, why does that matter? It shouldn't matter. If A promotes itself to candidate and then sends out a request, a vote request, then like D could come back and say like, oh, well, my latest log entry was at this index for term 7. But I don't think that actually it doesn't even say that, right? In the response to a request vote RPC,
it just says
it just basically says like its current term, which would be 7, which matches A's, because that's our hypothesis. And then,
Yeah, if A started the election, it will be in term 7. But D will not vote for A.
yes, that's true.
That's
But I
correct.
don't know. I think it's totally fine if D is alive and gives a response to A's vote request. Like,
Yep.
I don't think that deters A from being a candidate.
Someone just put in the chat, I think, the answer to that. So like Grant said that as soon as D rejects the vote, A will revert to being a follower because it will realize that it has a lower term number.
But okay,
Not necessarily, because again, remember that the most recent term on their log is not the same thing as the most recent term that the server keeps track of. You can have a higher current term than the most recent thing on the log. And so if A tries to elect itself in term 7, yes, when it tries to contact D, it will give up. But if A tries to elect itself in term 8, which it would if it's already seen that D has reached term 7, then like A can get elected.
wait, but if we assume that D is in term 7, like if A tries to elect itself for term 7, then we don't actually have this case because if the RPC request or response contains a term which is strictly greater than the current term, you give up. But if they're the same, then it doesn't matter. It will just proceed as normal.
That's correct.
Yes, that's true.
The entries get replaced by whatever A is telling it.
So at the end of section, like the election restriction section 5.4.1, they say Raft determines which of the two logs is more up to date by comparing the index and term of the last entries in the log. So wouldn't that mean that D has to become the leader if we're comparing?
No, because D just votes no, but other people might vote yes.
Yeah. So
what about the case where?
Go ahead.
What about the case where E runs for election in term 5, for example, or 5, yeah, and then it gets a vote from D saying no, it would then update its term, right, and stop running?
Okay, well, hold on. Like this, you're thinking about E is starting an election for 5.
Yeah, and if it gets a response from almost anybody, it's going to see that it's behind in a term, right? So it does update its term in that case, right? Even though it's not an append.
So another way to ask this question: who can become leader? Right? In this, from these, whatever, from these 6, A, B, C through F, who can become leader? Can F become leader?
No.
No.
All of them are up.
Can E become leader?
Also no. The only ones that can become leader are A, C, and D.
That's correct. Possible leaders.
But can A become a leader if D is alive? Because the safety section says that the request vote RPC implements the restriction that it compares the last log entries and the one with the highest log entry should become the leader.
No, I only think it doesn't vote for someone.
Exactly.
So like D will never vote for A, right?
That's
or
right.
for anything else.
That's exactly right.
I mean, it's also not true that like if you have an entry in a higher term than another node, that like you're actually sort of like better, right? Because I mean, you can be like becoming leader and trying to append entries into the log, but they like don't go through. So
well, if D is alive, it wouldn't go through. Okay, if D is alive, correct. D voted against, A becomes leader. A actually tries to, if A won't contact D if actually didn't vote for it. And so they would just proceed.
So why could D have logs in term 7 if it's not the leader in term 7?
D must have been the leader in term 7, correct?
yeah, I agree.
Otherwise, it would have no log entries.
When
Okay.
can you have log duplication? I think I forgot.
So in this case, was D a leader in term 7 who got disconnected and then the new leader got elected, the one at the top?
Yeah, I think so. Actually, let me take that back. I don't really remember exactly the sequence. I didn't really pay attention much to the top guy, but I presume that is the case.
It does say that is leader
Yeah.
for term 8 at the in like the right of the log.
I think the case we're looking at, the one where A has a higher term number than D, is the contradiction case in the safety argument they mentioned. Like, I think they proved that this is not possible.
That what is not possible?
Like that A could be elected, B missing an entry, and have a higher term than D, which is the case here. I think there's the step proof that this is a contradiction.
I don't think so. I think it's totally fine for it to be elected leader.
Yeah, I think the safety proof says that a future leader needs to have all of the log committed logs, and 7 is not committed.
Exactly. Like, there's a whole bunch of operations here that they're not committed, correct? They're just tentative. And so anything can happen to them. And nothing wrong will happen in the end.
And the reason that the whole committed thing works is because if it's committed, then more than the majority have those entries. And so someone who doesn't have the committed entries could never become elected, right?
That's correct.
Yes.
That's exactly right.
Yeah, they discussed like, yeah, like in terms of only someone who has all the committed entries can get elected. I think it gets more complicated with, you know, within the people who have all the committed entries, which ones can get elected. That's
Yeah, in some ways it doesn't matter.
Yeah.
So
Okay,
all the,
Thank you.
sorry, all the commits after term 4 are not committed then here, right?
So these 2 4s, those are not
Not
committed.
the first 2 4s.
Those are, what's the question? They will be committed.
Yeah, those would be committed, but then everything after wouldn't be. Yeah.
The 2 5s will be committed.
2 6.
And the 2 6s will also be committed.
Oh, okay.
We only need exactly half. It's okay.
Exactly half is okay. Okay.
Well, you need
no 1 over half.
4.
Yeah, so the 5s and 6 wouldn't be committed. Oh, but you have the you have the other leader, right?
Yeah.
Okay. Oh, let's not forget about those, right? I got it.
Okay.
Thank you.
I'll come back to this at the beginning of next lecture because some of you probably had to run to another class. But I'll come back to this. If you have more questions, feel free to stick around. And we'll resume this.
Can you say the log duplication again? When could there be log duplication?
What I meant is that the leader at some point forces its log on the followers.
I think you meant it on some of the previous slides.
Okay, so maybe again, I can't remember what I said. Sorry.
It is a little more, maybe a little more. Oh, it says they're deleted duplicates.
Detect duplicates.
Yeah, detect duplicates.
Yeah. This is not a Raft issue, correct? This is really a key value service issue, where a client request might be reached. A client might not get a response, even though that request actually went through Raft. Because what happened is that the leader maybe applied the operation to its state, but before it responded to the client, it crashed. So the client will retry and will send its request to the new leader. The new leader will run it through Raft and it will pop out of Raft again. And so it has to be the case that the KV server does duplicate detection.
Also, this is like only if the client didn't get the response that it retract.
Exactly. Yeah, exactly.
Okay. Okay, I see. Thank you.
Yeah, then there will be, no, you will do this in lab 3.
I think I also asked this question during the lecture, but I don't think I fully understood the answers. So I'll just repeat the question.
Yeah.
The question is that, so you said that the way commits work is that once the leader commits, it waits for a new client message, and then it just appends that message to the log entry and sends an append entry to the remaining followers with an additional message saying that they should also commit all the previous entries, correct?
Yeah, that's indirectly the protocol does that, correct?
Right. So my question is that what if the leader commits all the entries and right before it is able to send this message to the remaining followers, the leader crashes?
It cannot commit until it has a majority response from all the from the majority of the followers.
I see. So it first, like, even
it sticks it to its log, but doesn't actually deliver to the KV servers yet.
I see. So it waits from a reply of commit from all the remaining followers, and then it commits its own.
Yeah.
Okay. Okay.
Yeah. So there's basically this variable last applied or commit index, correct? That is actually maintaining. It only increases the commit index once it receives a response from the majority of the followers.
And all of the followers say that they have committed their own, like they have committed the log entries on their own servers.
They will commit their log entries once they know that the leader actually has committed it.
Right. So that's my question. Like, how would they know if the leader is unable to send that message to the remaining followers?
Well, yeah, so then, we end in situations that we just saw in this figure 7. There's going to be tentative log entries in their logs. And depending who becomes the new leader and what the log situation is, that operation may get committed or may not get committed.
I see. Okay. Yeah. Thank you.
Hi, I had a follow-up question on this. So if says the leader pushes a log entry, it gets accepted by majority, but it crashes. Then in later on, this log entry can be committed, right, by some other leader.
It can. It also may not.
Yeah, but say if it's get committed, then how does the new leader know who was the client who requested for this log entry, or how will the client be notified?
Okay, so there's really a question about like actually how the KV servers actually store their information with Raft. So the scenario is client talked to the leader, the client, the leader actually committed, did execute this operation or not? It did not.
No, it didn't.
It did not. Okay, so then one of the followers later will get this operation, maybe apply it, won't send a response because it doesn't even know about the client, but the client will retry, right? Because it actually hasn't gotten a response. It will contact the new leader and basically enter the same operation in the Raft again, and it will pop out again. And then the server will send as we'll see in the lab 3, it will send the last response. So in fact, the servers remember the last value that they sent back.
Okay.
So if there's a get request, the first get request is executed. There's no response to be sent back. That get request actually, but you will store the response in the KV server will remember the response. So when it sees the duplicate, it then will send the response. So there will be duplicate detection table that includes the response.
Okay, yeah, makes sense. Thanks.
You're welcome.
I was a little bit curious. I think I asked roughly this in my question, like pre-lecture question as well, like how Raft compares to other like consensus algorithms in terms of like optimizations you could do. And like as an example, I was thinking like the only thing I could sort of think of was batching.
Yep.
And it seemed like Raft is like perfect for batching because the leader could just like put more than one entry on its log, wait a little bit before sending its next append entries, then send that append entries with whatever batched set of operations or whatever it wants the replicas to do. So I was trying to figure out like what are sort of the deficiencies of Raft, like from a performance point of view.
Well, Raft does not do batching, correct? And maybe it could, but that would make the protocol more complicated. And so they decided not to.
I guess the way I happen to have written my like Raft lab code, like I sort of did batching implicitly because I would just wait a little bit sometimes before sending append entries. So I guess it felt like you don't really need to do anything other than just like maybe wait if you feel like it before.
Yeah, you can have multiple.
So yeah, I guess like.
I think it all comes down to performance. There's a whole bunch of optimization that Raft doesn't do, that some other systems do. Like, for example, you might be able to commute your operations because it doesn't really matter in what order you do them. So there's a slew of optimizations, and Raft does basically do none of them.
Okay. Thanks.
And it may be perfectly fine for like the use case, correct?
Right.
You mentioned something a couple minutes ago that a log entry could be lost. So is it possible that like a client request could never be executed, but with Raft guarantees that all the servers will execute the same set of log entries in the same sequence? And so like that means Raft cannot be usable for like all applications only if we can afford with some lost requests.
Well, we have to assume that the responses from the Raft service as a whole, correct? The KV service plus Raft may get lost anyway because the network gets lost. And that's the network may lost responses. So the client has to be able to repeat. Or the client must resend, must retry.
I see. So like when it actually commits a log entry and executes it, it replies to the client that it did actually do that.
Yeah. So this is like we were a little bit earlier. We talked about this the duplicate detection table. The duplicate detection table has the response that was sent or was constructed in response to executing that operation.
Thank you.
Any further questions?
All good. Thank you so much.
Hi, you're welcome. It's great to have so many questions.